Hello, we are a team from Jožef Stefan Institute competing on the GECCO unicost set covering problem competition. We start by solving unicost set covering problem exactly. The cover is built iteratively. Each set either is or is not in the optimal cover. Those decisions can be represented as a binary search tree. Branch and bound algorithm exhaustively explores the tree. It keeps a record of the best solution found yet. At the end, the best solution found is reported. Main feature of the branch and bound algorithm is that in some cases, it can be shown that a certain sub-branch cannot contain the best solution, and therefore that sub-branch does not need to be explored. Reduced space comes at the price of extra time needed to verify that a part of search space can be skipped. Determining which parts can and which cannot be skipped is not trivial, and this is the area in which algorithms differ the most. Exact version works very well on the smallest instances. The problem arises when the search tree, even with pruning, is still too big to explore in a reasonable time. If the algorithm is just stopped after some amount of time has passed, then all the work has been done on an arbitrary small subset of the tree, and all the explored solutions will be fairly similar. As such, the branch that contains the optimal solution might be completely missed, and found solution might be far from optimal. Therefore, instead of thoroughly exploring one part of the tree, whole tree is explored superficially. Instead of pruning only sub-branches that cannot contain optimal solution, branches that probably do not contain optimal solution are pruned too. Optimal solution might not be explored, but at least one near the optimum should be. Another approach we consider is splitting initial USCP into smaller USCPs. Solve each smaller problem individually, either exactly or with approximation, and then construct solution for a regional problem from sub-solutions. Splitting the problem correctly is a key to getting good final results. In order to explore as much of the tree as possible, algorithm is executed in parallel. Parallelization is achieved by offloading some sub-branches to some other available thread. That way, bigger part of search tree is explored and possibly better solution is found. On the table, we can see the results. Each test was run with parallelization on 8-core CPU with approximately 55-hour time limit. Exact algorithm has crashed on biggest instances due to a lack of memory, and therefore the number is missing. Approximate not only solved the problem with memory, but also produced slightly better results in most cases. While problem reduction in combination with approximation performs worse on academic instances, it improves on real-world instances.